Children, Sairam. Children, in the previous presentation, we have already started with the chapter States of Matter, and we have discussed the types of intermolecular forces, dispersion forces, dipole-dipole interaction, dipole-induced dipole, and hydrogen bonding. We have discussed the examples also of all the four types, and then I have told you that this year in standard 11 we are not going to study all the three states of matter, but we are studying only the gaseous state of matter. I have told you the properties of the gaseous state of matter, and we were discussing the gas laws. The four gas laws we have already discussed are Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. Now today I am starting with the combination of all the four laws, that is the ideal gas equation. This ideal gas equation comes out from the combination of all the laws. Now see, the three laws which we have learned till now, if we combine together to get a single equation, that equation will be called the ideal gas equation. Now according to Boyle's law, the mathematical form of Boyle's law was, at constant temperature V is inversely proportional to P. That means volume decreases when pressure increases. According to Charles' law, at constant pressure V is directly proportional to T. That means with the increase in temperature, volume also increases. And what Avogadro law says, it says that at constant pressure and temperature, the volume of a fixed amount of gas is fixed. So these are the three gas laws. Now if we combine the three gas laws, we get the equation V is directly proportional to NT upon P. Now removing the sign of proportionality, a constant comes, that is R. So we can now say that V is equals to R NT upon P. Now what is this R? This R is the proportionality constant and is called the gas constant. Now rearranging the equation, we get PV is equals to nRT. And R is the gas constant. It is same for all the gases. Therefore, it is called the universal gas constant. And this equation PV is equal to nRT is called your ideal gas equation. Now, what is the meaning of ideal gas equation? Ideal gas equation means that whatever the gas be, if it is following the equation PV is equals to nRT, that means that gas is an ideal gas. Now coming to the gas constant R, the value of gas constant R we can calculate is equal to 8.314 joule per Kelvin per mole. At standard temperature and pressure, the conditions used earlier, that is 0 degree Celsius or 1 atm pressure, value of R becomes 8.2 into 10 raised to power minus 2 liter atm per mole per Kelvin. Now children, the ideal gas equation is our relationship between the four variables and it describes the state of a gas. Therefore, is called the equation of states also. The ideal gas equation is called the equation of states. Now children, the combined gas equation, if there are two different gases, it can be, you can say, written as we can say that it is a relationship for the simultaneous variation of variables. If temperature, volume and pressure of a fixed amount of gas varies from T1 V1 and P1 to T2, V2 and P2. Then we can write down the equation as P1 V1 upon T1 is equals to NR for the first gas. Similarly, for the other gas, we can write down P2, V2 and T2 is also equal to NR. That means we can equate the two and we can say P1 V1 upon T1 is equals to P2 V2 upon T2. Now children, we are now in the state of solving a question. See the question carefully. At 25 degrees Celsius and 760 mm of Hg, when temperature is 25 degrees Celsius and pressure is 760 mm, a gas occupies 600 ml of volume. Now what will be its pressure at a height where temperature is 10 degrees Celsius and the volume of the gas is given? That means here again we can use the same equation where in the first case P, V and T all three are given. But in the second case it is asked what will be the pressure. Pressure is not given, volume and temperature are given. Now putting all these values, see children, you have to remember that the temperature here you have to put only in Kelvin. So converting 25 degrees Celsius to Kelvin will add 273 Kelvin. Now putting all the values, we can calculate the value of P2. P1 is 760. V1 is 600 ml, T2 is 283, T1 is 640 ml and V2 is 298. So children, putting all these values, you can calculate the value of P2 which comes out to be 676 mm Hg. Now I hope you are clear with the ideal gas equation or the combined gas law. Now children, Next, we can start with the Dalton's law of partial pressure. Now, what Dalton law states? It states that the total pressure exerted by the mixture of non-reacting gases, like for example in a container you have 2-3 gases, but the gases are non-reacting, they do not react with each other, then the total pressure is equal to the sum of the partial pressure of the individual gases. That means if in a container the container is closed, you have 2-3 gases, the molecules of the gases are not able to react with each other, then the total pressure which is exerted by the mixture of this gas will be equal to the partial pressure of gas 1 plus partial pressure of gas 2 plus partial pressure of gas 3 plus whatever the number of gases be. Now we all know that from ideal gas equation PV is equals to nRT. So we can write down the partial pressure of gas 1 will be equal to N1 RT upon V. Similarly, the partial pressure of gas 2 will be equal to number of moles of gas 2 into RT upon V. Similarly, for the third number of gas also, the partial pressure exerted by the third gas will be equal to number of moles of the third gas into RT upon V. Now putting these values in the equation, P total is equals to P1 plus P2 plus P3, we get P total is equals to N1 RT upon V plus N2 RT upon V plus N3 RT upon V. Now taking RT upon V as common, we get P total will be equal to N1 plus N2 plus N3 inside a bracket into RT upon V. Now if we divide P1 by P total, we get this. That means number of moles of, or you can say the mole fraction of the first gas. Now similarly you can also say that where n is equals to N1 plus N2 plus N3. Now it is called the mole fraction of the first gas. So you can write down P1 is equals to mole fraction of the first gas into P total. That is PA is equals to P naught A zeta A. Similarly, P2 will be equal to P naught 2 zeta 2, and thus the equation can be written as P1 is equals to zeta 1 into P total. That means for a mixture of gases, you can find out the partial pressure by using the mole fraction, and if you are knowing the total pressure also. Now children, I hope you have understood this Dalton's law of partial pressure. Children, the ideal gas equation, that is PV is equals to nRT. PV is equal to nRT. That means for an ideal gas, when pressure multiplied by volume will give you N into R into T. Now, this equation you all know we have derived on the basis of gas laws. Now, the kinetic molecular theory of gases is actually explaining the behavior of the gases, that how gases should behave in order to obey all the four laws and obey the equation PV is equals to nRT. So, I am starting with the kinetic molecular theory of gases now. Now children, we all know that according to the gas laws, when the pressure is increasing, the gas compresses. That means when pressure we are increasing, the volume of the gas becomes low. But actually, what is happening at the molecular level when the gas is compressed? A theory is constructed to answer such questions, and the theory is a model, that is a mental picture that enables to better understand our observation. We all know that when pressure is increasing, volume also always decreases. But what is happening at the molecular level is explained by the kinetic molecular theory of gases. Now we will be discussing the assumptions or the postulates of the kinetic molecular theory of gases. Now you have to remember, whenever we are talking about the kinetic molecular theory of gases, we are talking about the atoms and molecules which cannot be seen. Hence, it is said to provide a microscopic model of the gases. We are now studying the microscopic model of gases. We are talking about the atoms and the molecules. Now children, according to the kinetic molecular theory of gases, the gas consists of large number of identical particles. They can be atoms or molecule. They are so small and so far apart that the average actual volume of the molecule is negligible to the empty space between them. They are considered as point masses, and this assumption explains the great compressibility of the gas. So, what we can say, according to the first postulate of kinetic molecular theory of gases, there are many molecules. You all know that the gas molecules are far apart from each other, and many molecules are there inside this, and the actual volume which is occupied by the molecule of the gas is negligible compared to the total volume of the gas. You have to remember this statement. Later on, some important thing about this statement we are going to discuss. So remember, the actual volume of the gas is negligible compared to the empty space between them. Now coming to the second postulate, what second postulate of the microscopic model of gases says? There is no force of attraction between the particles of the gas at ordinary temperature and pressure. That means when temperature and pressure are ordinary, then the gas molecules are not attracting each other. The support for this assumption comes from the fact that gases expand and occupy all the space available to them. If we put the gas inside a container, then the gases are not exerting any force of attraction. The molecules of the gas are not exerting any force of attraction on one another, and if I'll open the lid of the container, all the molecules will go here and there. That means there is no force of attraction between the molecules. Now coming to the third postulate, according to the third postulate, the particles of a gas are always in constant random motion. That means the particles of the gas are always moving here and there inside the gas. If the particles were at rest and occupied fixed position, then the gas would have fixed shape, and which is not actually observed. You all know gases do not have a fixed shape. Now coming to the next postulate, that is the particles of the gas move in all possible directions in straight line, and when they are moving, then they collide with each other and with the walls of the container. Now the gas pressure is a result of the collision of particles with the walls of the container. This is why the gas exerts pressure. The molecules, when they are moving here and there, they collide with the walls of the container. Now the next is collision of gas molecules is perfectly elastic. What is the meaning of perfectly elastic? Perfectly elastic means that the total energy of the molecules before and after the collision remains the same. There is no loss of energy during the collision. There may be exchange of energy between the colloidal molecules and the individual energy may change, but the sum of their energy remains constant. That means the molecular collisions are perfectly elastic. If there were loss of kinetic energy, then the motion of the molecules would have stopped and gases would have settled down, but this never happens. That means when the gas molecules are colliding, they are not giving out energy. Only interchange of energy between the molecules is taking place. Now next is, at a particular time, the different particles in the gas have different speeds. That means some particles are moving with more speed, some are moving with the lesser speed, and their kinetic energies are also different. This assumption is reasonable because as the particles collide, we expect the change in speed. Like for example, this is one of the particle, this is another particle. This particle is coming to this side, this particle coming to this side. When it hit one another, then there is an exchange of energy. Even if the initial speed of the particles were same, the molecular collision will disrupt this uniformity, and as a consequence, the particles must have different speed, which goes on changing constantly whenever a collision takes place. It is possible to show that through the individual speeds, though the individual speeds are changing, the distribution of speed remains constant at a particular temperature. Next is, if a molecule has variable speed, that means if a molecule is having different speed, then it must have variable kinetic energy also. Under these circumstances, we can talk about only average kinetic energy. In kinetic theory, it is assumed that average kinetic energy, we are talking about the average kinetic energy of the gas molecule, is directly proportional to the absolute temperature. You all know this is obvious. With the increase in temperature, the kinetic energy of the gas molecule increases. It is seen that on heating a gas at constant volume, the pressure increases. On heating the gas, kinetic energy of the particles increases. It strikes with the wall of the container more frequently and exert more pressure. Now this was all about the kinetic molecular theory of gases. Now children, you have to remember, kinetic molecular theory of gases allows us to derive theoretically all the gas laws studied in the previous session of the chapter. Now calculations and predictions based on kinetic molecular theory of gases agree well with the experimental observation and does establish the correctness of this model. Now children, you have to remember the gas laws. We have to remember the kinetic molecular theory of gases. But in the next presentation, we'll discuss the deviation from the ideal gas behavior. Deviation from the ideal gas behavior means all the gases do not follow the PV is equal to nRT equation. Now, why they don't follow? We'll discuss this in the next presentation. For today, we'll wind up. Thank you and Sairam.